Wonderful. So again, if you want to know more, if you during the day you're like, oh, I wonder how they did this, you can get the MiSBIE Mother paper and learn all about this. A few years, as we were running MiSBIE, we started to think about the energetic cost of living, being alive, the energetic cost of mitochondrial disease. And Gabriel, a student in the lab, did this study where he asked, how much energy do cells spend just to stay alive if their mitochondria don't work properly, right? So very similar to what Evan was asking, but here in a very controlled, simple system in cells in a dish. And what we found here is that OXPHOS, or cells that don't have the oxidative phosphorylation machinery working normally, burn about double the amount of energy, right? So, and you look at the cells also, they look tired, they don't divide very quickly, they don't seem to do as much kind of on an outer appearance, yet internally, they're running about twice the metabolic rate. What's happening? And then we did a meta-analysis where we looked at multiple studies and from the literature where VO2, VCO2 had been measured in individuals with mitochondrial disease when they're like on a bicycle before they do exercise, but they're not resting, sitting down doing nothing or kind of in bed reading. And what we found there is that on average, these people spend 30% more energy just to stay alive. And then in a much better controlled study, this was a motivation then to do MDE. In MDE, Evan is finding 10 to 15% increase in energy expenditure, right? So the basal cost of being alive, of sustaining your bodily functions, is about 10, 15% higher. And perhaps higher if you start to move and if you engage in other things. So where could this come from, right? So we're going to think about this biologically. And here's a system where you have the organism, which is a larger container than the cell and then the mitochondrion. And what happens when the oxidative phosphorylation, the electron transport chain inside the mitochondria don't work properly because of a mitochondrial DNA point mutation or deletion, the electrons don't flow as easily, so there's more energy resistance in the mitochondria. This sends signals, mitochondria send signals to the nucleus. They say something's wrong. We need more of us. We need more mitochondria. We need more antioxidant machinery and so on. This can trigger it in stress responses. The best studied stress response in that context is the integrated stress response, ISR. And then there's also a program that kicks in called mitochondrial biogenesis, right? The genesis of new mitochondria. Well, this costs energy. Making a new mitochondria costs energy. I'll echo some of what Evan said earlier. So then this triggers compensation. The cell also is increasing its ability to do glycolysis and other pathways that cost energy. And then the nucleus starts to produce proteins. We heard about GDF15, FGF21, and other ones. These, when you look in the blood, they look like biomarkers, but really the cells attempt to talk to each other, right? Something is wrong energetically. I need to let other cells know in this cellular collective, which the body is. It costs energy. So there's an increased cost of having a mutation inside the cell. There's intracellular signaling, right? The mitochondria talking to the nucleus and nucleus talking to mitochondria and the other organelles. And then there's also an increase in ATP consumption overall, right? As a result of this. So that we could call cellular efficiency, decreased cellular efficiency, right? It costs more energy just to have the cell do what it needs to do because at the same time, it's also activating stress responses. This would lead to what is called clinically hypermetabolism, right? Metabolism is the flow of energy through the metabolic pathways that then we can kind of measure this, and that's the cost of life. If you're burning more energy than you should to do the same thing, then that's called hypermetabolism. Clinically, typically in the clinic, 10% above baseline for a whole human being is considered kind of the threshold for hypermetabolism. So hypermetabolism is going to kick in back into the organism to sustain this higher metabolic rate at the cell level. The heart needs to beat faster, right? And the liver needs to do more work. And other organs also start to work harder. If there's lactate, GF15 in the blood, those biomarkers then signal onto target cells. And if you're a cell and you receive a signal like GDF15 or a growth factor or an interleukin or whatever it is, you're going to burn energy just to receive that signal and to process that information, the signaling cascades intracellularly. And then as we've learned about, there's psychosocial factors, a human experience, right? There's a mean-looking evaluator in front of you. You have to give the speech. Well, this is going to increase your heart rate, and it's going to make you feel like, you know, your sense of self, your ego is threatened. And then you release cortisol, that costs energy. And then your blood pressure increases, that costs energy. And then you start to sweat, that costs energy. Your hairs on your arm, rise, that costs energy, little muscles pulling on the hair follicles. So everything costs energy. So we can understand now, I think there's a clear path for how subjective experiences translate into an energetic cost, right? And the organism level, at the cell level. And then all of that together leads to a change in physiological efficiency, which is what Evan talked about. Hypermetabolism in the dish is linked to accelerated cellular aging, probably for reasons that relate to this phenomenon Evan mentioned, where you have activated stress responses, the sympathetic nervous system, and then that steals energy away from other things, growth, maintenance, and repair, the anti-aging processes. And then there might be systems levels constraint, right? If you activate your stress system, your sympathetic nervous system, you start to run, you need to sprint, what happens to the digestive system? You shut it down, right? And that happens through a variety of mechanisms. So there's a deprioritization or reallocation of energetic resources and organ systems. And that might relate to what we call post-exertional malaise, right? Patients who exercise after they feel terrible. And that might relate to this prioritization, reprioritization. And then the fluctuation in symptoms and the exacerbations and after infections or after kind of challenges like this. So this is an energetic model to understand the pathophysiology of mitochondrial disease. Why do patients who have impairment in the mitochondrial electron transport chain have disease? The traditional model, which is on the left here, says that if there's a mutation, it breaks a protein. If the protein's broken, then the mitochondria can't make ATP, and then there should be ATP deficiency. It's actually not proven in vivo in living individuals that there's actually a loss of ATP. So we don't believe that would drive symptoms. But then this model says then this is what causes symptoms and then pathologies and premature death. So that's kind of a bottom-up reductionist model, right, which is very much in line with the central dogma of biology. On the right-hand side is an energy-based model, right? It's the same problem, the same symptoms we're trying to understand, but here we have a deeper level of insight into the energetic cost and trade-off that might be operating under the hood. So this has changed how I think about mitochondrial disease, and then we suspect also this applies to other health conditions, right? A disease is an organ or a system in the body that's not working optimally. It costs energy. When something is not working optimally, it costs additional energy to bring that back into normal function. So perhaps this is kind of a common ground for a lot of pathophysiology and why if you have one disease, you're more likely to have another disease, right? This could be because that the existing disease is sinking energy and then stealing that away from other processes. So what does this mean for mitochondrial disease and for human health in general? And I'm just going to briefly mention like 5 or 6 potential issues that have been issues in mitochondrial disease, mitochondrial medicine for a few years, which may be an energetic understanding of those symptoms to help clarify. One is that many mitochondrial diseases are more severe in childhood. And we haven't talked about this, but if you look at the energy expenditure during the human lifespan, when you're an adult, from 20 to 70 years old, it's pretty flat. There's only one part in the human lifespan that has much higher energy expenditure, and it's in childhood. Between age 2 and 10, when there's this rapid phase of growth, and you're learning about the world, you're building your personality, building your body, going through these life transitions, very expensive. And so there's data from a few years ago, beautiful paper in Science showing this. So perhaps the severe childhood diseases that we see in mitochondrial diseases and that some children actually grow out of in the case of Pearson syndrome. So there's a process there that might be related to how much energy it costs to be a child. Patients experience often fatigue, sleep, and need to nap frequently. And like Evan mentioned, perhaps that's to compensate. If you're burning excess energy, the signal, GF15, and maybe probably other signals, are signaling onto the brain to say, take it easy. Like you're burning overtime. This is not sustainable. And then the response to this is to feel sick or to feel tired and to want to sleep. In some patients, alcohol trigger fatigue and decompensation. And many patients avoid alcohol kind of intuitively. They've learned early on, alcohol is not good for me. And that could be because alcohol consumption actually increases basal energy expenditure, exacerbating hypermetabolism. So if you're already hypermetabolic and you have a glass of wine or 2 or 3, and then your basal metabolic rate, the energy you need to survive, increases 10, 15, 20%, this is bad news. And maybe if you're healthy, you have this nice reserve, bioenergetic reserve, you can afford to do that. And if it relaxes and kind of slows down your sympathetic nervous system, maybe overall it's adaptive. That might be where the data that a bit of alcohol is good for you. But if you have a mitochondrial defect that is making you hypermetabolic, maybe that's why you become intolerant. Infectious conditions often can trigger clinical exacerbation, symptoms onset, and even mortality. So the leading cause of mortality is infectious conditions in mitochondrial disease. Why is that? Well, turning on the immune system is very expensive. So there might be competition there. And finally, psychological stress may trigger or exacerbate symptoms of mitochondrial disease. And the activation of stress responses cost energy. We haven't quantified this in MiSBIE. I wish we could have, but there's data in the literature that says anywhere from 9 to 67% increase in basal energy expenditure, right? When there's this nice spike in cortisol, nice spike in GDF-15, the reduction in FGF21 to make room for other pathways, all of these things are happening at the same time and it costs energy, probably a significant amount of energy. So there's outcome variables in MiSBIE. I'll switch over to more general things. There are mitochondrial type outcomes. I'm just showing this. I don't want to go into details. You're not meant to read this, just to give you a sense of how rich this is. Mitochondrial outcomes, stress reactivity, allostatic load, multi-omics, neuroimaging, clinical, psychosocial. This is a treasure trove, which our participants allowed us to collect. Our team diligently collected, and our funders, made possible. So we want to make the most of this, and we're still in the process of analyzing and generating data, and we're looking for collaborators who have questions to ask. And in the next session after this, we'll ideate around this. Biomarker analysis, some are completed, several are still in progress, like I said, and we have planned analysis. For the first time, we'll know what the human stress proteome is and the human stress metabolome, right? What happens energetically, metabolically in your body when you respond to mental stress? And there's a biobank available for emerging markers. So in terms of using MiSBIE samples and data, there's the parent MiSBIE R01 mandated the deposition of some data in the NIMH data archive. So this is all there already. Future omics data will be deposited in GEO, so standard kind of accessible. This is, I think, nice for scientists, non-scientists, not so much. All other data is harmonized and in shareable form in REDCap. And in development, there's a data request form, and there should be an online portal, maybe early next year. Caroline has been leading this. Vanessa has been helping, and Grace Liu, our data manager, is going to be orchestrating this. So we hope that there's some form that you can go on the MiSBIE page and say, I would like to analyze data for this, and then you can fill out the form, or if you wanted samples and you have a lab and you can analyze some data, then you can request those as well. MiSBIE is part of an ecosystem of studies that we've developed over the last 10 years. And MiSBIE is probably the richest and broadest and most ambitious. But there are other things that have synergized, and you heard about the mitobrain map this morning, and the mitochondrial psychological stress study that was run in Pittsburgh that validated some of the MiSBIE findings, the cellular lifespan study, the aging hair study, the mitotyping work. So all of this is coalescing. I want to point out 3 that I think are relevant. We just heard about MiSBIE, which ran from 2016 to 2023, and now we've been for 2 years in data analysis mode. The MDEE study, which just closed a few months ago, and Evan has been hard at work analyzing that data and writing the first manuscript and sharing this with the world. And then there's the mitobrain ROS map, which extends some of the mitochondrial phenotyping into a bigger cohort. Cynthia, who you heard from earlier, took on the massive challenge of analyzing 5,000 human brain samples. So very soon we will have the most extensive mitochondrial profiling data sets in the human brain with just absolutely beautiful longitudinal data, retrospective data of psychosocial measures in those individuals. So lots of potential. And the goal of doing this is we have important psychobiological questions to ask about mitochondria and states of mind and the mind-mitochondria connection. But then we're going to make this data available to the ROS-MAP community and to the rest of the scientific community to ask some other questions. I'm going to finish by saying a few words about health and why I think we should really care about this and why this matters. This is a little person here and different states of health. where you have, optimal health, disease-free, you can be hanging on, or you can be clearly sick and something's wrong. Typically, kind of health proceeds like this. You're okay, then you get sick, then you're kind of hanging on, and then maybe your symptoms or resolved in some way, but there's still something there. That's what we end up calling chronic disease. And that's a very lucrative state for the current system of disease care and healthcare that we have. What we would want to do is something like this, where you get sick, and then after you can actually recover, right? You can move from hanging on to being disease-free and being in optimal health. This is also when people grow. There's something called post-traumatic growth, right? You're exposed to a difficult experience, and somehow you can learn to grow from this. And maybe you change your behavior, maybe you change your outlook on life. And so there's a lot of growth physically and mentally, maybe spiritually, that can happen through those transitions. This is the healing process. The basis of health is our ability every day to heal little things, your mitochondria, your cell membranes, your body, your mind. And we don't really have a science of this. And it feels like mitochondrial psychobiology and the hints that you've heard about today, that the mitochondria and the energetic regulation inside our cells is actually related to how people experience life. I think are hints in that direction of building a science of health and building a science of the healing process. So healing, I'll finish on those thoughts. Healing is a set of dynamic, energetic processes by which the organism moves towards optimal function. Right? This is intentionally a broad definition. And very important here, it's dynamic. Like health is not a thing, health is a state. And it changes over time, and healing is the basis for that. Healing can manifest as growth and development in childhood, for example. It can manifest as a recovery from injury and trauma in adulthood, and adaptation that enhances the organism's coherence as a whole. So even if you're not diseased, there's still the opportunity to heal and to grow. And healing, importantly, should also be extended to social and communal contexts. We're not little isolated creatures. We're all connected. And we are social organisms that are moved by other social organisms. And the kind of thing we do today is connect at some level, and we create something better than each of us is individually. And I feel like this is the same kind of movement that also we see in nature, and how different organisms are interconnected, and how we're connected to the living world, and that gives us oxygen for mitochondria, and then we give CO2 to the plants to continue thriving. So I'd like to say thank you for this wonderful day. Thank you to all the presenters, all of our team members who've done this, those who are here and those who are no longer. It's been a great ride. Now we're gonna have a poster session after this, and before the poster session, we're gonna take a break. So you can stretch and take a deep breath, activate your mitochondria a little bit. And then when we're back, we're gonna have a little discussion, dialogue at each of tables where you're sitting. And then we'll think about what kind of scientific questions, what kind of problems should we tackle, and how should we do this? And there's going to be a little prize for this. And then after we do this, then we'll have drinks, and I think the beverages are getting ready, and the food for the evening. And then we'll have a nice little celebration. So thank you again.